Okay, welcome back. So today we'll continue our discussion on the genome assembly topic, and in particular we will look at genome assembly using de Bruijn graphs. So remember that we have been looking at the genome assembly problem in this module, where you are given as input a set of reads. So you are given a set of reads as input, and the goal is to reconstruct back the original genome sequence from where these reads were sampled from. So we'll continue this discussion on new algorithms or alternative algorithms for how we can reconstruct this genome sequence accurately. The approaches that we have seen so far have been these two. That is, first we looked at finding shortest common superstring using maximum weight Hamiltonian path in an overlap graph, and the second approach that we looked at was a greedy algorithm, which iteratively joins reads with maximum suffix prefix overlap length. Now both of these approaches follow a parsimony principle, that is, these are based on the principle that maybe the shortest string that is compatible with the reads should be the genome sequence. In other words, we have been saying that maybe the simplest sequence which is compatible with the read should be the genome sequence. But we saw some examples in the last lecture where we said that if you have long repeats in the genome sequence, then the output of these algorithms tend to give shorter sequence as output. So if you have true genome sequence G which has long repeats, then the output of these algorithms can sometimes collapse the repeat copy, where you have maybe only a single instance of the repeat. So unfortunately, because of this limitation, state of the art assemblers do not use either of these two approaches because of the repeat collapsing issue that we saw in the last lecture. So because these were the first formulations for genome assembly, we started by looking at these formulations. But from this lecture onwards, we will now look at fundamental techniques that power modern genome assemblers. In particular, the focus of this lecture will be on the assembly algorithms using de Bruijn graphs. We will look at what is a de Bruijn graph, and then how do we use de Bruijn graphs for genome assembly. So let us get started. Now de Bruijn graphs are named after a Dutch mathematician, Nicolas Govert de Bruijn. It is defined as following. So you have a, let us say, a fixed integer k, and you have a set of reads as input. Then the de Bruijn graph is a directed graph constructed as following. So you have in this graph vertices are all the k-mers, that is substrings of length k observed in the given set of reads. So these are all substrings of length k observed in the given set of reads, and these form the vertices of the de Bruijn graph. And edges correspond to suffix prefix overlaps of length k minus 1 between k-mers. So this is a very simple definition, and that is why this is a very simple as well as powerful data structure. So let us look at a simple example. Let us say you have only a single read is input, and your parameter k is equal to 3. Then given the above definition that we just said, for this read input, your vertices will be ACT, because as I said, vertices are all k-mers, that is substrings of length k, and if you have k equal to 3, then your first vertex will be ACT and your second vertex will be CTG. So you have only two vertices in this graph for this example, and we will have a edge, directed edge between these two vertices, because there is a suffix of length 2 which matches a prefix of length 2 of the second vertex. So, I hope the definition is clear, and we will look at few more examples that will give you an intuition of the properties of de Bruijn graph. So, let us say we see a second example where let us say you have 3 reads as input. Now, this time again assuming k equals to 3, that is the parameter k equals to 3, then for this particular example you can see that we have 4 vertices, that is ACT, this is the first k-mer that we observe in the read set, then you have another vertex CTG, then you have another vertex TGC, and then you have a 4th vertex GCC. So, in total there are 4 vertices if you have these set of reads given as input, and accordingly based on the suffix prefix overlaps you can draw the directed edges and you get the following graph for this example. Now, let us look at one more example here where we have sequenced reads at higher coverage. So, that is we have sequenced every position in the genome multiple times and we have more redundancy in the data set. So, for this example observe that the de Bruijn graph remains unchanged, that is even if you add more redundancy in the data set the graph remains unchanged, because remember that the k-mers are derived or these vertices are derived from the set of k-mers observed in the read set. So, even if you have multiple copies of a k-mer it will still correspond to a single vertex in the graph, because for vertices we are looking at set of k-mers. So, duplicate k entries are not allowed, and therefore, in the compared to the previous example the graph remains unchanged. Let us see another example, in this case where we have a sequencing error. So, let us say in one of the reads there is a sequencing error, and then how would such sequencing errors impact the graph topology. So, in this example it turns out that the sequencing error led to a creation of a new vertex in the graph TGA and a new edge in the graph. Now, as you can imagine, when you have real world data sets where you have many sequencing errors possible, then these sequencing errors can make the graph analysis difficult, because you have many edges and many vertices in the graph which should not have been there actually. So, this through this example I am conveying you that sequencing errors can lead to new artificial edges and vertices in the graph which can make the downstream analysis complicated. Now, throughout this course I have referred to presence of sequencing errors, but I have not given you actual reason of why sequencing errors crop up in practice. So, why is it so difficult for the sequencing instruments to produce these reads without any error? So, I thought let me take a short detour and give you an example of why these sequencing errors crop up in practice, and for this I am taking nanopore sequencing technology as an example. So, there are many sequencing technologies out of which nanopore sequencing is one of them, and what happens in the way we read the genome sequence or the way reads are generated is how basically you have DNA molecules passing through nanopores, and as the DNA molecules pass through these nanopores you have these current signals being generated, and these current signals are shown in light blue color in this animation, and as output, so these current signals are saved by the instrument on the computer processor, and through these electric signals we have to infer what the DNA sequence would have been. And it turns out that depending on the composition of the sequence passing through the pore, these electric signals will fluctuate. So, the modeling is done in a way to infer the genome sequence corresponding to these electric signals. Now, as it turns out, because of this process, so because we have to infer the DNA sequence from these electric signals, several factors can make the sequence interpretation challenging. That is, for example, there can be signal fluctuations in practice. The speed of the DNA molecule passing through the pore can vary, and there can be chemical modifications on DNA molecule which can also affect the electric signals. And as a result, producing reads which are error free is extremely challenging in practice, and that is why sequencing errors like this crop up in real data. So, modern genome assemblers would always address these sequencing errors, and maybe they will have a pre-correction step that will first try to correct as many errors as possible before moving to the genome assembly step. Okay, so that was a short detour that we took for explaining why sequencing errors occur. So, let us come back to the De Bruijn graph examples. Here I am showing you another example just to illustrate the effect of repeat in the genome sequences. Now, here I am showing you an example where you have a string substring CTG repeated twice in the genome sequence. So, your actual genome sequence may be ACTG, CTG, AT, and your CTG pattern is repeated twice. Now, in this case, what happens to the graph topology when you have such repeats in the genome sequence? So, the bottom at the bottom we have shown how the graph topology looks like, and you can see how the repeat has created a loop like structure in the graph. And this is intuitive, because what would happen is you would have what is ACT, then you would move to CTG, then you would move to TGC in the graph, then you would have GCT, and then you would come back to CTG. So, such repeats will form loop like structures in the De Bruijn graph, and again these loop like structures make the downstream analysis of this graph more challenging. We will see why this happens, like why am I saying that downstream steps become more challenging, because you can imagine that as the graph becomes more denser, then the analysis of this graph, that is interpreting the true genome sequence from this graph, can become challenging. For example, given this graph only, it would be difficult to tell how do we interpret the walk that corresponds to the true genome sequence. So, if in my walk, should I traverse this loop once, or should I traverse this loop twice, or so on, and this information will be not available from this graph alone. Now, as it turns out, because of this real world challenges like repeats, sequencing errors and so on, the real world topology of these graphs is extremely challenging. So, in an ideal scenario, you would want to see a simple chain like topology where you can read the genome sequence from left to right in a single go. But when you have such dense graphs, reading the genome sequence from these graphs is not trivial. So, this is just to show that even if we build these graphs, we still have to do more work to interpret the genome sequence and to reconstruct the genome sequence from this graph. So, this particular graph is built from a bacterial genome data set, and if you want to download the read dataset, you can go to the NCBI website, enter this accession ID, and you will be able to download the read dataset yourself. In practice, genome assemblers would try to use multiple heuristics to clean the graph. By cleaning, I mean simplifying the graph, so that we do not see many tangles and many loops in the graph, and the genome sequence interpretation becomes easier. Okay, so let us move forward. Now, so far we have discussed the definition of de Bruijn graphs, but once we have constructed these de Bruijn graphs, the next question is how to use a de Bruijn graph for genome assembly. For this, let us use some basic notation. So, I will assume that given a read set S and parameter k, I will denote the de Bruijn graph as dbks. So, by parameter k I mean that the k-mer length is k or the substring length is k, and the input set of reads is capital S. So, the de Bruijn graph built for this parameter and this input is noted as dbks. We are going to make couple of assumptions, that is, we will assume that every k-mer of the genome is included in some read, that is there is no coverage issue. So, we have covered entire genome sequence during the genome sequencing, and every k-mer of the genome is included in some read. Secondly, we will assume that there are no errors in reads, that is every k-mer observed in the read set is correct. There are no corrupted k-mers in the read set. So, for example, we saw an example here. So, we are basically assuming that there are no such reads with errors. Now, given these observations, so given these assumptions, we can make the following observation, that the target genome must be a string spelled by some walk in the de Bruijn graph that visits every vertex at least once. Because we are connecting every adjacent k-mers whenever they have k-1 suffix prefix overlap length, and we know that every k-mer of the genome has been sequenced, you can easily see that the true genome sequence must correspond to some walk in the graph, and because there are no errors in the reads, we should cover every vertex in the graph at least once, right, and because of the repeats we may need to cover some vertices twice or thrice, but that is a separate issue. So, from this line we can say that the target genome must be a string spelled by some walk in the de Bruijn graph that visits every vertex at least once. Now, this observation alone does not give us the genome sequence, because there can be many walks in the graph that are vertex covering. So, how do we formulate a problem that gives us the genome sequence as output? Well, we can again try maybe the parsimony principle, that is we can assume that maybe the simplest solution is correct. So, if we go with the parsimony principle, we can define the problem formulation as following. So, as input we are given a set of strings S, that is the reads, and we have an integer parameter k. So, this gives us the de Bruijn graph as well. As output we want the string spelled by a shortest walk of de Bruijn graph that covers every vertex at least once. So, the parsimony principle comes from the fact that we are asking for a shortest walk, that is we are asking for a simplest solution that covers every vertex at least once. So, let us look at this formulation in more detail. As first question we can ask, can we solve this problem efficiently? Like, do we have an efficient algorithm for solving this problem, or can we come up with an efficient algorithm to solve this problem? So again, I am stating the problem formulation on the top. We are looking for a shortest walk in the de Bruijn graph that covers every vertex at least once. Now unfortunately, as it turns out, that finding shortest vertex covering walk in a general directed graph is an NP hard problem. However, in our problem formulation, we are working with special graphs which are de Bruijn graphs, and de Bruijn graphs have special properties. That is, we have vertices that are k-mers in the read set, and we are only adding edges when you have k minus 1 suffix prefix overlap. So there is a possibility of having an efficient algorithm that is applicable to only de Bruijn graphs. And in this case, as it turns out, that for de Bruijn graphs, yes, we can transform this problem into a simpler problem which can be solved efficiently. The key idea is as following. We will build another graph G in which every k minus 1 mer will be a vertex. So every k minus 1 mer observed in the read set is a vertex, and the way edges are added in this graph is following. That is, for every k-mer in the read set, and an edge is added from its k minus 1 length prefix to its k minus 1 length suffix. Let us look at the example at the bottom to understand this better. So you have again a single read A C T G, and let us say you have parameter k equal to 3. So graph G will look like this, where the vertices are built from k minus 1 mers, that is 2 mers. So the 2 mers are AC, CT and TG. The edges are now built from looking at 3 mers in the read. So your 3 mers in the reads are ACT and CTG. So for 3 mer ACT, we will add a edge from AC to CT. So for this you will add an edge from AC to CT, and for the second 3 mer CTG, you will add an edge from CT to TG. So this is a slightly different definition. So this is not a de Bruijn graph the way we defined before. This is a slightly revised definition, that is the way we are building this graph. So we are building the edges from the 3 mers and we are building the vertices from 2 mers. Now why are we doing this? Well, it turns out that we can solve the main problem that we want to solve by looking for a shortest edge covering walk in this new graph G. And as it turns out, for finding shortest edge covering walk in a directed graph, we know efficient algorithms that are fast. So this is equivalent to the Chinese postman problem, which is a standard problem in graph theory, and for this problem we know fast algorithms. So if you want to learn more about the Chinese postman problem, you can refer to this Wikipedia link and see what algorithms exist for this problem, but we will not go into further details because there are standard libraries and implementations of this algorithm that can be used for solving the main problem that we want. So once we have mapped this to a shortest edge covering walk problem, we can leverage the existing concept from graph theory to move forward. How do we prove correctness of this argument? Well, observe that we wanted to find a shortest vertex covering walk in the original de Bruijn graph, and way we are saying is that we will build another graph G using k minus 1 mers as vertices, and in this revised graph G we are going for shortest edge covering walks. Well, intuitively at a glance you can see why we are saying that, because now we are constructing. So, there is a one-to-one correspondence between an edge of G to a vertex of the original De Bruijn graph. So, by covering edges in G, implicitly we are finding a vertex covering walk in the De Bruijn graph. So, mathematically we can prove the correctness as following, that is, we can prove that computing string spelled by a shortest covering walk in De Bruijn graph is equivalent to computing string spelled by a shortest edge covering walk in G. And the proof technique will be that if you have a vertex covering walk in De Bruijn graph, which is say of length L, then you can compute a corresponding edge covering walk of length L plus 1 in G and vice versa. So, I am only giving you a proof sketch, I am not giving you the entire proof in this slide, but the intuition is as following. So, for example, if your vertex covering walk is, let us say, GAT, ATT, TTA and so on, the way I can correspond this to an edge covering walk in graph G is by splitting this. So, let me use another color. So, the way I can build a equivalent edge covering walk in G would be to split this into two mers, that is GA, AT, TT, TA and so on. So, you can split this into two mers and you can build an equivalent walk of length L plus 1 in graph G, and you can show that if your walk in the De Bruijn graph was vertex covering, then your walk in graph G will be edge covering, because you have a one-to-one correspondence between the vertex of De Bruijn graph and edge of this graph G. So, I will only give you the intuition for now and I will leave the details for you to figure out. We will move ahead and ask another question about this algorithm. Okay, so there is one last point I missed, that is, once you establish this correspondence between vertex covering walk and edge covering walk, all we need to do is find the shortest edge covering walk in G and spell the sequence out of it. So, in this case the shortest edge covering walk is shown in light blue color, and once you have the shortest edge covering walk, you can spell the string that is spelled by this walk. And remember that when we are spelling this string, we have to count these suffix prefix overlaps only once. So, for this particular example, the output sequence will be GATT ACA TTA CAA. Okay. Now, we have established that this problem can be solved efficiently usually by transforming it into an edge covering shortest walk problem. But another important question is, can we use this formulation in practice? That is, again, if we apply this on real data that is satisfying our assumptions, then can a biologist trust the output of this algorithm? Well, let us look at one limitation of this algorithm. It turns out that unfortunately multiple optimal solutions may exist in practice. So, even when we are solving this problem, the optimal solution may not be unique, and if we just pick one arbitrarily, then we are unlikely to get the target genome sequence. This is clear from the example shown below. So, if you think of this example and if you think about the shortest vertex covering walk in this graph? Well, you can see that maybe one way to build the shortest vertex covering graph is to take A, then B1, then C, then D1, then E, then F1, then you will have to go back and then you will have to cover B2 because these were left uncovered, then D2 and then F2, and then you can proceed to H. However, observe that we could have easily chosen in the first walk we preferred B1 D1 F1 sequence, but we could have picked any other sequence, that is B2 D1 F2 or B1 D2 F1 and so on. So, we had to make an arbitrary choice when we reach this vertex, and again we had to make arbitrary choice when we had reached this vertex. And for this particular example you can see that there are 2 raised to power 3 optimal answers, because there is a binary choice that we can make at each of these 3 vertices. And if we just pick arbitrarily one of the optimal answer, then you can imagine that there is no guarantee that the output sequence will correspond to the correct true genome sequence. So, as a result, this is one major limitation of this formulation, that if we just solve the problem optimally and there is no guarantee that the output is going to correspond to the correct genome sequence. Now, you may ask, okay, why are we considering this graph with bubbles, like why should bubbles exist in a graph? Is this just an adversarial example, or do these bubbles also appear in real world? Well, it turns out yes, the bubbles are a very common structure that we observe in real world de Bruijn graphs, and here is an illustration to support that argument. So, suppose you have a genome sequence in which you have 2 near identical repeats, which is common in large genomes, that you will have many near identical repeats in the genome sequence. Now, for this example, observe that if you build a de Bruijn graph with k equals to 3, then you will observe that because of this mutation in the repeat sequence, you would have a bubble like structure in the de Bruijn graph, because there is a difference, local difference of vertices in this local region, but here you have common vertices on the left and common vertices on the right. And as a result, because these vertices are common, you will have common start vertices before the bubble, and you will have common sink vertices after the bubble, and between them you will see a bubble like structure because of the sequence difference that is present due to this mutation. So, this C2G mutation in the repeat sequence creates a new bubble like structure, and because of this is fairly common in the entire genome sequence, you will have many near identical repeats. As a result, you will see many bubbles in real world de Bruijn graphs. So, going back to our argument, we cannot directly use the formulation because of this ambiguity, that is, we cannot pick arbitrary optimal solution and give it to the end user. So, what do we do then? Well, so far what we have seen is that all known formulations where we are aiming to output a single sequence, we have observed limitations in all such formulations. For example, the shortest common superstring, the greedy algorithm, and then even the finding shortest vertex covering walk in a de Bruijn graph. All of these formulations have limitations, and in this case what do we do? Well, should we just give up, or should we think of other way of addressing this problem? Well, maybe we can reduce our aim, that is, we can maybe relax our ambition, and we can maybe start not aiming for the entire genome sequence, but maybe we can target portions of the genome sequence as output. So, here is the intuition, like think of all possible genome assemblies, that is think of all possible strings that can be spelled by the vertex covering walks in this graph. Then observe that in all such possible reconstructions, the string spelled by path B1. So, if you just look at the string spelled by path B1 locally, it must be a substring of all possible genome assemblies, because if you think of any vertex covering walk in this graph, then B1 has to be a substring of all those walks. What we can do instead is we can return a set of safe strings, that is all possible assemblies include these safe strings, right. So, for example, in this example you can think of that, okay, maybe A is a safe string, because any vertex covering walk should have A as a substring. Similarly, H is a safe string, because the entire string spelled by this subpath H should be a substring of all possible genome assemblies. So, instead of giving a single genome sequence as output, we are giving a set of safe strings that are guaranteed to be substrings of the original genome. And the hope is that we can give long safe strings to the user, so that they can still make useful biological inferences from these safe strings. So, to formalize this idea, I need to give couple of new definitions, that is one, unitig. Unitig is a path in the De Bruijn graph where vertices have exactly one incoming edge and one outgoing edge, with an exception that the first and last vertex can have any number of incoming and outgoing edges. So, example, like you can see that, for example, A is a unitig, because this in this path all the vertices not counting the first and last have only a single incoming edge and a single outgoing edge. Similarly, you can observe that G is also unitig. A single vertex is also unitig, right, because by definition single vertex or any path of two vertices is also unitig. Now, accordingly we can define maximal unitigs, that is they cannot be extended in either direction. So, for example, I can say that this vertex is a unitig, but this is not a maximal unitig, because I can extend this towards left and I can extend this towards right. So, a maximal unitig will be this entire path in the graph, because this I can, so once you have this entire path I cannot extend it further without violating the unitig property. So, if I extend it further, let us say I consider EF1, then there is a vertex in the middle which would have the number of outgoing edges S2, which would violate the property of your unitig. So, EF1 is not a maximal unitig, but E is a maximal unitig. So, I hope this example is clear, that is we are looking for some kind of safe strings that we can pull out of this graph, and for that we are defining something known as maximal unitigs, which are these chain like structures that we see in the graph. So, in this particular example A, B1, B2, C, D1, all these paths shown by alpha, these characters are all maximal unitigs. Moving ahead, here is one more example where I am showing you again a maximal unitig. So, this is a maximal unitig, this is again a maximal unitig, and this is again another maximal unitig. Observe that you cannot extend any of these further, because otherwise we will violate the property of the unitig. Okay. So, why are we defining these Unitigs? It turns out that we can make a claim that all these maximal Unitigs are safe. That is, if you, so remember that a source is a vertex which has no incoming edges in the graph, and a sink is a vertex in the graph which has no outgoing edges. The claim is that if the De Bruijn graph has at least one vertex covering walk, if it has at least one source vertex and at least one 6 vertex, then a Unitig in the De Bruijn graph must spell a substring of the target genome. So, that is, these Unitigs are safe output to be given to the user, and that is they spell the substring of the target genome that we want. So, what we want to claim is that these Unitigs are safe and there is no ambiguity here, and this can be given, the user can trust this output from the program. How do we prove this claim? Well, the proof is as following. We will use induction. So, assume that your Unitig is denoted as V1, V2 until Vp, and let G be a vertex covering walk of De Bruijn graph that spells the true genome sequence. So, G is the vertex covering walk corresponding to the true genome sequence. Now, observe that G must begin at source and must end at sink vertex, because source has no incoming edge and sink has no outgoing edge. So, in that case the G must begin at source and G must end at sink, otherwise we will not be able to cover the source and sink vertices in the walk. So, this is a simple observation. Then we will prove using induction that Unitig U must be a sub walk of G, and if we can prove that Unitig U is a sub walk of G, then it proves the claim that the string spelled by Unitig is a guaranteed to be substring of the target genome. So, let us see how the induction argument works. Well, the base case is simple, that is, if you have a Unitig which is a single vertex. So, we are inducting on the length of the Unitig, and if your Unitig is a single vertex, then obviously U has to be a sub walk of G, because G is vertex covering. So, it must visit U. Now, the induction hypothesis is that the claim holds for all Unitigs of length up to p minus 1, and therefore, the hypothesis gives us that V1 to up till Vp minus 1 is a sub walk of G. Now, how do we prove the main claim, that is, the entire Unitig is a sub walk of G? Well, observe that Vp minus 1 has an outgoing edge to Vp, and therefore, Vp minus 1 is not a sink vertex. As a result, when the walk G reached Vp minus 1, it cannot terminate at Vp minus 1 and it must continue to Vp, right, because remember that Vp minus 1 has only a single outgoing neighbor. So, Vp minus 1 has a single outgoing neighbor, that is, it has a single outgoing edge to Vp because of the definition of Unitig, and if your walk G reached here, then it must continue to Vp as well, and that proves that Unitig is a sub walk of G. So, that this induction argument proves the claim that Unitig must spell a substring of the target genome. Therefore, what we can do as an algorithm is we can output basically simply all the maximal Unitigs from the De Bruijn graph, and which requires a simple linear time traversal of the De Bruijn graph, and you can easily output all the strings spelled by the maximal Unitigs from this graph. So, in this case the maximal Unitig output will be basically A T A A, C A. Similarly, you will output a second string to the user, which is ACAACC, and you will output a third string to the user, which is ACATTG. So, this will be the final output that you would give to the user if you are outputting maximal Unitigs to them. And we can say that these Unitigs are guaranteed to be substrings of the target genome under the assumptions that we have made. So, this completes the analysis of de Bruijn graph algorithms, and I hope you are convinced that de Bruijn graphs are useful for genome assembly. In fact, they are used in modern genome assemblers. In next lecture, we will look at more algorithms that are used in practice, that is overlap graphs, multiplex de Bruijn graphs, and we will also see what is the role of latest sequencing technologies in shaping the field of genome assembly. Thank you.